Hi, everyone. I'm Samson Rainey from AG's press office. Thank you for joining us for this media roundtable at AbSciCon24 in Providence, where we'll hear about NASA's Europa Clipper mission from a great slate of panelists. We'll begin with the panelists giving brief presentations describing their work, and then we'll open up to questions from reporters. This format is meant to be more informal and conversational than a press conference, so feel free to have a back and forth conversation and ask a lot of questions. Our discussion is being recorded and will be available to the public later today, posted on AG's YouTube channel. For press, slides will be made available after the event. We will end after an hour or whenever there are no more questions. Let's see. Charles, did you want to introduce the panelists? Would you like me to introduce? Okay.
I can introduce.
Oh, excellent.
Yeah.
I'll pass it off to the panelists to begin.
Thank you so much, Samson.
Cool.
Hi, all. Thank you so much for being here today. We're really excited to be talking to you all today about the Europa Clipper mission. If I can get the next slide, please. I am Dr. Lindsay Hayes. I am the program scientist for astrobiology at NASA headquarters. Today, I'm going to be talking to you guys a little bit, or I'm here to answer questions about the context of the Europa Clipper mission within sort of NASA's astrobiology program, the search for life, why Europa itself as a planet, or as a moon rather, is important to our understanding of habitability and different habitable environments in our solar system, why it's important for our understanding in the search for life off of our planet. We also have Dr. Vance from NASA's Jet Propulsion Laboratory. He's going to give us some big picture context of Europa for the mission. We have Dr. Ingrid Daubar, Jet Propulsion Laboratory and Brown University, who will be giving us a little bit about mission status and architecture. And then Dr. Elizabeth Zibi Turtle at the Johns Hopkins Applied Physics Laboratory, who will talk about the payload on the Europa Clipper mission and the camera. So I'm going to hand it off to Steve to get us kicked off. Thank you.
Okay, yeah. Thanks, Lindsay. Hi, everyone. Thanks for taking the time. Excited to share what we have about Europa Clipper. So just some context. I'm here presenting about Europa Clipper at the AbSciCon meeting. We're at a special place just on the eve of launch of Europa Clipper, in which we get to share a lot of the exciting details about the mission, including the design of the overall approach, why we're doing Europa Clipper in the first place, which is our overall goal is to explore Europa to investigate its habitability. And so yesterday and today, as it turns out, I'm presenting about a paper that I led as part of the habitability assessment board on Europa Clipper in my role as a former co-chair of that group. Our goal is to shepherd the data of Europa Clipper together in order to piece together the picture of Europa to understand its habitability. So the big effort, lots of team members involved in that. Building on that theme, I can tell you a few things about Europa in the context of Europa Clipper. We can go to the next slide. Sorry, if we can go back just real quick. I just want to emphasize, this information here about this paper is about one of many papers in this issue of Space Science Reviews, and I encourage you to check out those papers. These are the details of Europa Clipper that we've been working on for many years, and they're now available for people to see. Okay, so about Europa, why are we doing this? So Jupiter's moon Europa, next slide, may create the conditions for life in its global ocean. So this is a moon of Jupiter about the size of our moon that somehow has possibly more liquid water than in all of Earth's oceans. And as you can see in this picture, this stylized picture of Europa with Europa Clipper flying over, Europa's surface is geologically very interesting, likely has been active for a very long time, and it might not be that thick. There might be materials for life just under the surface. When we first conceived of this mission, we wanted to know, is there an ocean, and could there or could there not be life there? That was our definition of habitability. Since then, I like to think that we've refined that. I think the field of astrobiology as a whole has refined habitability as the first rung in the ladder of our search for life in the solar system. And we have a lot of different ways that we can understand the habitability of Europa. That is, what kinds of life might be there, and how long they might be there, and how those might have changed. Those conditions might have changed through time. And so, understanding Europa means understanding it as a system, globally as well as locally. So we go to the next slide. I'll share a figure from our paper, and this is showing that beautiful surface of Europa indicating all these different really interesting geological features that we think link to overturning within the ice, possibilities of liquid within the ice, possibility that ions, micrometeorites, irradiated materials generated at the surface make their way into that ocean, and that the circulation in that very deep ocean, 60 to 100 miles deep, causes the ocean to make those materials from the surface interact with materials from the deeper interior. It's possible there's volcanism, or there was volcanism in the deep interior of Europa, which might also generate materials that are the perfect complement to the oxygen-rich materials being generated at the surface. And we can draw a direct analogy to conditions where life in Earth's oceans is able to make a living independent of direct energy from the sun. So with that, I'll turn it over to the next panelist.
Okay, so if you could show my first slide. So I'm Ingrid Daubar, and I'm really just reporting from a really big team of people that are very excited to announce that we are 5 months from launch, and we are go for launch. The Europa Clipper mission, Steve has done a really great job explaining why we're going there. Maybe I can do a little bit about how we're gonna get there, because Jupiter's hard, right? I mean, all of space is hard, but Jupiter's extra hard. It's really far away, it's dark. There's a really toxic radiation environment that's especially damaging to electronics, and everything we're sending is electronics. So we really, these fantastic engineering teams at JPL and APL have built this really amazing spacecraft. The scale of it is just enormous. We can go to the next slide. I encourage you to go to this website, europa.nasa.gov. There is a live webcam so you can see this spacecraft. It's hard to describe just how big it is because every time I see it, I think, how is it so big? But there's a live webcam showing the clean room where it's being built and assembled. And there's usually people working in there, so you can see the people for scale. But this whole thing, once the solar panels are arrayed, it's about 100 feet long. The bus itself is, 2 or 3 stories tall. And the complex electronics are just mind-boggling. So it's a really advanced mission, really cutting edge technology. And what we're doing, one of the reasons that the solar panels have to be so big is because we're so far away. We're 5 times further away from the sun than the Earth. So there's not a lot of solar radiation out there. So we need really big solar panels. We need a really big antenna to send all that data back to Earth. And we designed the mission so that we kind of dip down into these radiation fields of Jupiter. We fly by Europa really quickly, and sometimes really closely. The closest flybys are 25 kilometers from the surface, which I find terrifying. And then so we dip down, we use all of our instruments. We have a really great suite of 10 science investigations that Zibi's going to mention a little bit more about. And they are going to gather science in a coordinated fashion. So we have these collaborative data sets that will work with all over all different wavelengths of light and energy, fields and particles, gravity science. We're going to learn everything we can about Europa in this really quick flyby, and then we're going to swoop out into this long pedal rotation where we kind of recover from that radiation dose, send all those data back down to Earth, and then plan for the next flyby. So we're going to do that about 50 times, and we're going to learn a lot about Europa on the way. So let's see. So all of these, we talked about, I mentioned that we have 10 science investigations. All of the instruments have been delivered. The spacecraft is ready to be shipped to Kennedy Space Center. This will happen in the next few weeks. So this is kind of your last chance to see that spacecraft before it's going to go to space. So go to the website and check out that Clipper cam. We are on track for this October 2024 launch. So we're really excited.
Thank you. If you go to the next slide. So I'm Zibi Turtle. I'm the principal investigator for the Europa imaging system, which is the cameras. We have 2 cameras on board the spacecraft, and as Ingrid was saying, right, and Steve, this is a very large team of individuals. This is part of the camera team after delivery of the second camera to be integrated onto the spacecraft. So everyone's very happy that we passed that milestone. But just for, for context, there, like 700 people worked on the cameras alone on this mission. So there's a really large group of very dedicated people that has been working on this mission for quite a while. If you go to the next slide, that shows kind of the suite of instruments we have on board the spacecraft. And at the lower left, you see a view of the spacecraft. So this is from the live camera that Ingrid was talking about. In the far left of that, you can see a couple people, which gives you a sense of the scale of the spacecraft itself. We just finished an optical test, so I was actually following along on the live camera as much of the camera team was to see how the test was going. So let's see, there's a red rectangle, and right below that, you kind of see well, that's the camera. You're looking down the aperture of the camera. So that dark aperture is looking into the narrow angle camera. You can see all the instruments are blanketed up on the spacecraft there. Getting ready for shipping for launch. So there's a suite of instruments addressing all these different aspects of Europa as a system. The ones in green are remote sensing. We have imaging from very short ultraviolet wavelengths through visible and near infrared, and then out into the longer thermal infrared. So that's the Europa UVS, ICE invisible, MISE is the IR spectrometer, and then Europa Themis, the thermal imager. And then we have a ice penetrating radar as well that's going to give us a view into the subsurface ice of Europa, which is going to be really exciting. And we also have a suite of in situ instruments, mass spectrometer, dust analyzer, magnetometer, instrument to study the plasma environment, as well as gravity and radio science, and instrumentation studying the radiation environment. So it's going to be a really comprehensive view of Europa and the environment that it's in, to give us an understanding of the system and really get at the nature of the conditions inside Europa and investigate its habitability. The next slide just talks a little more about the imaging that we're going to be doing. The two cameras allow us to image during these very fast flybys Ingrid was talking about. When we're, very close to Europa, we can do very high resolution imaging and then context imaging as well. One of the things we want to understand is the possibility of exchange through the ice shell, as Steve was showing in that beautiful graphic that I always love seeing. We don't know how much or how often there could be exchange between the ocean and the surface, and so that's one of the things we want to study. And so the cameras in particular are going to not only image and map the surface, but also measure the topography. And so we'll have this 3D view that's then complemented by the subsurface sounding radar that'll really get at the nature of the crust and the processes acting in the crust. One of the things that we forget, or maybe we don't forget, but one of the things that we see pictures of Europa fairly often, and we don't always realize that only like 15% of Europa has been imaged at better than 900 meter pixel scale. This is a large scale, or 14% at 400. So you can see there's only like 1% between that half kilometer and kilometer pixel scale. And so with Europa Clipper, we're going to map over 90% of Europa at 100-meter pixel scale. So this will give us a really good view of the geology of Europa and the interplay of the different geologic processes. And so that image at the top right shows the scale of what we'll have 90% of Europa imaged at, which is going to be spectacular. And then we'll also have color data and the stereo topography data, and we'll be searching. Many of the instruments can search for actual current activity in the form of plumes that could be erupting through the Europa shell. And then just at the very bottom on the right is Antarctica. That's not Europa. We haven't seen Europa at this scale yet, but we're really excited to do it. ICE is going to be able to image several dozen sites of Europa at this scale, at better than 1 meter scale. So, resolving the table and chairs here in the room, and it's going to be really spectacular to understand the detailed geologic processes and to understand Europa as a system, and everything that's happened there and that might be currently happening still.
Fantastic. I think those are the slides that we had. Is this you as well?
Oh, that just illustrates, if people were interested, the coverage, so that you can see on the left, the reds and oranges are the higher resolution Galileo coverage, and using that same color scale is what we'll get with Europa Clipper. So it's really gonna revolutionize our understanding of the nature of the surface and the subsurface, and this mission as a whole with the very complementary coordinated instrument suite is going to give us a very interdisciplinary view of Europa and how it works.
Literally and figuratively, a whole new perspective.
Yes, yes.
See if there's, there we go, we're taken to the end. Okay, well, thanks, panelists, for sharing your work with us. We'll now open it up to questions from reporters. As a reminder, only registered reporters may ask questions. And if you would prefer to ask your question without speaking, type your complete question along with your name and affiliation to the chat, and we will ask it on your behalf. I will end the discussion after about 45 minutes, so when there are no more questions, whichever comes first. I will just kick it off with maybe an obvious question, and maybe this was overlooked by me. Why a flyby rather than a landing mission?
Yeah, I can take that. So we would love to land on Europa, right? And someday we will. But that's even harder than this flyby mission. The radiation environment there is really, really dangerous. I heard that if a person was standing on the surface with no radiation shielding, the radiation alone would kill them in something like a few minutes to a few hours. So this is not an environment that is conducive to mechanical or electronic things. So it's a very difficult and very expensive mission to do. So and also we just don't know as much as we would like to know about Europa. As Zibi was saying, very small portion of the surface has been imaged at a resolution that at least I would feel comfortable landing on. You know, we're kind of used to landing on Mars at this point, but Mars has been studied in so much detail. We have meter scale imaging of any place we might want to land on Mars, whereas we only have that in like one little postage stamp on Europa. So there's a lot of things we don't know that Europa Clipper is going to tell us that will help that lander when it does happen. Like, what is the nature of the surface? What is the roughness? What is the porosity? Are we going to land on like crazy ice spikes in all directions, or is it going to be a nice, smooth little snow surface? So we really want the data from Europa Clipper to inform that future landed mission, and also to pick the best site, because we might only get one shot, right? So we want to pick the most scientifically interesting site and the safest site, and Europa Clipper is going to tell us that.
So I'll just say as well, from a NASA perspective and from an exploration perspective, one of the ways you can think about sort of exploration is, the first thing you do is you do a flyby, then you do an orbit, then you land, and you think about having a lander and that sort of thing. And then as we're thinking about and watching sort of Mars as a model, then you think about roving on the surface, and then you think about sample return. And each of those things along the way, sort of like you were saying, Ingrid, tells you a little bit more that you need to know to have a successful following mission. And so, this is the next stage, is to do this, this sort of dedicated, flyby orbit kind of hybrid, so that we can get that information. So it's the next step along the way.
And one of the great things that was done in studying this mission was coming up with a Jupiter orbit that gives you flybys distributed globally around Europa, so that you can get the global view over a longer term mission without being embedded in the Jovian radiation environment. Because if you were there in orbit at Europa, the mission could only last 2 or 3 months because of the high radiation environment that Ingrid was talking about. So this is, as you say, it's a hybrid, and it really enables the global view, but the longer temporal scale as well. So it's very
but
exciting.
weirdly, and in contrast to this NASA vision of like moving toward landing, it was the innovation here was to be able to do the orbiting science with multiple flybys.
Exactly.
Yeah.
Exactly. And I think that's fantastic.
Yeah.
It's one of many sort of innovative things that are part of this mission.
Cool. Any questions from reporters in the room?
May I ask a
Charles.
question? will Europa Clipper be close enough to encounter anything that could be considered part of an atmosphere of Europa? Is it potential to encounter ice grains that are in space or anything that could be more directly sampled as opposed to just the remote sampling of studies by flybys?
Yeah, I can take the first part of that answer. So when we talk about an atmosphere at Europa, we need to be careful because, you know, on our atmosphere on Earth, you can whoosh your hand through it. It's collisional. There's not going to be atmospheric friction at Europa. We do hope that there might be some kind of plume-like activity that will inevitably be different from the plumes that we saw at Enceladus. And Europa Clipper is designed, as Ingrid mentioned, to fly very close to Europa and to sample materials coming from the surface. And so in that sense, we will absolutely have the chance to sample materials lofted from the surface. Yeah, and it's expected that instead of an atmosphere, Europa has some kind of exosphere. So molecules that are not colliding, that are nevertheless gravitationally bound to the surface. And team members on Europa Clipper have used computer simulations to map out that atmosphere, including how the atmosphere would look if there were remnants from temporary ejecta. So even if we don't fly directly through a plume, any kind of short-lived activity, we'll probably be able to pick up some clue to that and characterize the materials coming out.
Yeah, and if we go to the slide with the instrumentation, if we can do that. We have a whole suite of in situ instruments. I think they're the ones
Yep.
circled in red.
Right.
So we have a mass spectrometer that's gonna measure the volatiles. SUDA is a dust analyzer that's gonna look at particles of dust coming off the surface. And we're gonna look for plumes everywhere. We hope that there'll be, this fantastic plume and we'll just happen to fly right through it. But even if that doesn't happen, micrometeorites are impacting the surface all the time. And they're kicking off particles that SUDA mass specs will be able to tell us what the composition of those are, and then therefore what the composition of the surface is. So we're really excited about what those are gonna tell us.
Yeah.
Great. I have a question from Aditi Ramakrishnan from AP. Steve Vance, you mentioned that the definition of habitability has been refined over time. Could you say more about how astrobiologists define it today and how that will factor into what we're looking for on Europa?
Sure, thanks for the question. So I mentioned habitability as I think it was conceived maybe 20 years ago as kind of a binary. And this has been a strong talking point for me in the recent years that we need to think of it as not just a binary. But on Earth, we know there are environments where different types of life can live. We increasingly know that there are categories of extremophiles, organisms that can live in acidic pools of brine that we would ourselves definitely not want to live in. And so, while it's exciting to think about looking for life somewhere or understanding whether life could be there, the history of Earth is replete with life evolving along with the geological history of Earth. And so we can ask questions about the dynamic habitability of Europa, how its habitability might have changed through time. Just to drive that point home, NASA Astrobiology and Planetary Science has really embraced that terminology. So we're prioritizing understanding dynamic habitability in the coming decade.
And all I'll just add, from the astrobiology program perspective, habitability is one of the things that we try to understand on multiple bodies within our solar system. So Europa Clipper is trying to understand that for Europa, but a number of our missions at Mars have had a similar sort of a goal objective is to understand what the habitability in the past was like on Mars and the potential for those types of habitability to have extended through that Martian history. Other missions that we have, Europa Clipper, Dragonfly and other things, habitability is a big part of that question as well. What does it mean to be habitable? Habitability certainly has multiple aspects, not just temperature and environment and energy and all those kinds of things, but also time. How long has a place had conditions that may be favorable to habitability? And every time we go and search for life and we don't find life, that also informs us about habitability. Well, it helps us to refine our concept of habitability and what we know and what we don't understand yet.
And one of the things we're really fortunate about, maybe all solar systems are like this, but our solar system has this diverse array of worlds that have very different histories and different conditions. And that allows us to
Exactly.
study habitability in these very different contexts. And as you're saying, to understand what conditions are, conducive, what conditions are necessary, and what conditions might prevent the development of a habitable environment. And
Yeah.
so I'm always struck by just how fortunate we are with this wide range of worlds to explore.
And planetary science has certainly allowed us to explore many different worlds already, and only more as we can hope for.
You. Any questions in the room? Faith?
Are any of the instruments gonna be aimed at finding sort of potential signatures of life as well as just, or is it just habitability? I wonder if you'll have the opportunity, if there was life, to at least maybe make some measurements that could pick up.
I can also respond. Well, I wanted to touch on the instrument suite. Ingrid emphasized we have these two mass spectrometers. These are incredibly innovative. I just want to express my excitement for this mission. We're taking capabilities that have never flown into space. We're taking something that's analogous to a really capable mass spectrometer that you would have in your lab, for those of us that have them in our lab. And we're flying it over the surface of Europa. While the goal is to understand the chemistry that drives Europa, including the possible metabolisms that might happen in Europa's ocean, that mass spectrometer and the dust analyzer as well have the possibility for picking up larger organic molecules, including amino acids and things that might be clues to the presence of life, though not definitive evidence of life itself.
Yeah, it's as Steve was saying, the instruments are really designed to understand the habitability, to understand the nature of the environment and the potential there. But there's been a lot of work done to understand what kinds of chemical biosignatures exist and how to detect them. And it's definitely been an area of active research because we kind of think, as you said, of life as kind of a binary thing, but detecting life is not necessarily binary or easy at all. And in fact, one of the talks yesterday, they were talking about the fact that for the first 2 billion years, I think, of life existing on this planet, it might not have been possible to detect that life was here using remote sensing observations. And so that just really, it's really striking that the complexity of life, but then also the complexity of what you need to be able to do to detect it.
And I'll add another concept or another idea from the sort of astrobiology program perspective. And I'm going to talk this way so that gets picked up by the microphone, but I'm sorry, but I'm going to back to you. But the general thing is that, one of the things that we have realized in the search for life missions that we have had so far and are sort of thinking about the search for life is the understanding the context in which you make a measurement relative to the search for life is really, really important. It's really important that you understand the environmental context in which you are making that measurement, because that can give you a lot of additional information, whereas sort of simple bare measurement can have a lot of ambiguity. And so one of the great things that this mission will do is help us understand some of that context. So as we think about future missions to Europa and we think about what, after this mission is wildly successful and gets all this great information back for us, we can have that next mission and design that next mission with a better understanding of the context, so that when we think about the search for life, we really understand what we're looking for and in what environment we're making that measurement.
Any questions coming online? Oh, go ahead.
I'm going to ask you guys a question. I would just like to know the thing that we talked a little bit about of the innovations, all the great things they're part of this mission. I want to know the innovation that you guys are most excited about for this particular mission.
Okay, I can talk about some of the
Everybody's looking at
innovations
you,
for the
Zibi.
cameras. Right, the cameras are actually really a huge leap in capability from previous cameras that we've sent on planetary missions. So one aspect of that is that the detectors are very large. They're actually 8 megapixel detectors. That doesn't actually sound large compared to one's phone. But for a planetary mission, that's pretty good. Most of them are, kind of Cassini had, 1 megapixel. So, the cameras use the CMOS technology for the detectors, which means that we can do imaging in different ways. So we can do kind of, the way you take a picture of your camera, right? You can take you can point it and target it, and the narrow angle camera actually has a gimbal that allows us to target and build up coverage of Europa that way. But we can also do what's called push beam imaging, where you match the imaging to the pace at which the spacecraft is moving over Europa. So this is what HiRISE does at Mars, and you build up these great swaths of images. It's kind of like what you do with your phone if you're taking a panorama, actually. So we can use these different modes, which is really important with a flyby mission architecture, to be able to do imaging at the different distances and speeds over Europa, because the flybys are not only very low, but very fast, 4.5 kilometers a second. And so we're reading out this very large chip and getting data, but we'll have color observations that way, and the stereo as well.
I think it's so cool how the WAC gets the 3-line stereo at the
Yeah.
same time.
So
Yeah.
exactly. So the WAC is actually the wide angle camera is actually taking like 6, 7, 8 images at the same time. And then those can all be combined to have a multicolor and stereo topography, a digital terrain model. So that's going to be, from a camera perspective, the capability is going to really be excellent in terms of getting data. It's going to be very complicated to plan, but it's going to be really excellent in terms of data and the way this fits together with the complementary data set, right? There's been a lot of development as well in sounding radars we've sent to other places. We haven't sent one, a sounding radar to an icy world, and understanding that structure within the ice shell is just going to tell us so much. This unseen terrain underneath the surface. So that's some of the areas that I'm really excited about in terms of the new capabilities to take advantage of in the outer solar system.
I have a question. So Zibi, you're the Dragonfly mission, going to Titan, and I know we're on different time frames. That one's much later. This one's gonna land when? When is this one gonna?
2030.
Okay.
It's not gonna land.
Get
to Jupiter in 2030.
I was just wondering what interesting insights from this mission, Europa Clipper, may help understand what you're expecting to find at Titan with Dragonfly. If there's any commonalities, anything that you can gauge from this mission, that would help that.
So Dragonfly is a mission to Saturn's moon Titan, which is also an ocean world. It has a deep interior liquid water ocean. Europa's is much shallower, as Steve was talking about. Titan is unique in that it has an atmosphere. None of the other satellites in the solar system have an atmosphere, and the atmosphere has very complex carbon chemistry in it. And so at Titan, we have a kind of a different opportunity to study how far organic synthesis has progressed in this environment that has sunlight driving this photochemistry, and then those products having the opportunity to mix with liquid water. So Dragonfly is a landed mission that will explore the surface of Titan, flying from place to place to make chemical measurements of the surface composition and that chemistry. So they sound like very, very different missions. But this is part of that comparative planetology, that we have the opportunity to do in the outer solar system. And I think especially aspects of the interior ocean, the dynamics of the ice crust that we may learn about with Europa Clipper, and the nature of habitability, as we've been talking about, right? This is an evolving science. It's a very new science and it's an evolving science. And so I think a lot of understanding from Europa Clipper is going to provide that key context that we were talking about for the measurements on this very different ocean world at Saturn. So I think there will be more commonalities than we maybe tend to think about when we think about these very different worlds.
Well, if I can jump onto your response, we've talked about Europa Clipper being the thing we do before our next exploration of Europa. We hope to land in the future. Well, Dragonfly, we're landing on an ocean world, right? And I'm delighted that there's going to be a seismic package.
Yes.
And we can figure out the activity of the interior, things that we can figure out about the interior of Titan in a different way than we would at Europa, and practice, hopefully,
Yes.
doing that at Europa in the future.
Yeah, seismology on an ocean world is going to be very interesting and very different from what we're used to, right? We're used to, silicate worlds, and these ocean worlds with the seismic signatures in a solid shell over a liquid water interior are very different, and it's going to be fascinating to see what we learn with Dragonfly, and then what, as you say, what that takes forward to future exploration, landed exploration of ocean worlds.
Excellent.
Question.
Yes.
So launching in October, you get to 2030, is there any plan before arrival, any science that's gonna be done in transit, like that opportunities?
There's science in transit, yeah, sorry, I'm gonna talk this way.
What?
Alright, so the trajectory is not straightforward. We're gonna get 2 gravity assists, we're gonna go by Mars, I think in 2025, and Earth actually in 2026, before we go out to that outer solar system to reach Jupiter. And those will give us, little kicks to help accelerate the spacecraft out there. So right now, we're not really planning too much science, but we do want to make sure all the instruments work. We're definitely going to do calibrations and checkouts. We want to make sure they work together. Some of those calibrations we're hoping to do at Mars. And hopefully everyone will wave as it goes by Earth. But there's also, it's a long cruise, it's 6 years. Most of the scientists aren't going to be thinking about Europa too much during that cruise, but we're hoping to do a little science on the way. So yeah, but the big show is going to be in 2030.
Great. I don't see any questions online. Any other questions in the room?
Well, yeah, you were asking what are excited about for
Yeah.
Europa Clipper, among the innovations. I mentioned the mass spectrometer and a lot of other exciting things about the instruments, but what I'm thinking about lately is the amazing fact that we're going to try to characterize the ocean using magnetic fields. So the reason we think there's an ocean there today in the first place is because Galileo, the previous spacecraft, flew by Europa close enough 4 times to get a sense of the magnetic response. So this is like Europa walking through a metal detector at an airport, except Jupiter is a metal detector. It's creating this field that Europa then responded to, and the near surface signal was from the dissolved ions in the ocean, right? So that's like the metal. I guess if you walked through a metal detector with a bottle of water with salt in it, that would also set it off. So this is like walking through a metal detector multiple times to figure out what kinds of salt are in that bottle of water. Right. And so we've designed the mission to have these multiple flybys to sample different parts of the magnetic response. And so by figuring out the strength and the timing of the response relative to Jupiter's driving field, we hope to actually figure out the salinity of the ocean. I think that's just kind of mind blowing.
It is really good. Do you have a? Yeah, well, one thing I wanted to talk about, it's not so much an innovation, but the very human nature of this mission.
Yes.
This is the biggest team I've ever worked with, right? Zibi said 700 people just on the cameras, and we have 10 of those investigations. So the number of people and the way that we engage, not just the team, but we're trying to engage the public. And we've done that. We've had the opportunity to work with a lot of really great students. We have a special relationship with the University of Puerto Rico, where we've had people those students come to our meetings, which are usually kind of closed doors, and experience that. And I think that's really great because this is it's a long timeline. To get to the outer solar system takes a long time. So these students that are students now are going to be like running things when we get there. And maybe some of us will be retired. We'll see. And certainly by the end of the mission. So I think that's really great. And there's been a lot of concerted efforts. And one of the ways that we're trying to represent that as a symbol to kind of send out into the universe is this plate of
Yes.
metal. It's bolted onto the vault, which is this like radiation shielded box full of electronics. And it's made of the metal tantalum, which I love the name of because it doesn't sound real. And I saw them on the Clipper cam just maybe last Thursday or Friday. They bolted it on, so it's officially attached and it's going to go to space. And it represents, it's intended to represent all of the kind of human aspects of this search for life and the connection that we have with water. So there's a theme of water running all through it. The outside of the plate has the words for water in over 100 different languages represented as waveforms. So if you go to that website, you can hear all of them and see the waveforms, which also kind of ties into that seismic investigation. So those vibrations and what that sound is like. And then on the other side of the plate, there are everything is done by hand, which I think is really cool. There is a microchip that has the names of over 2.6 million. Yep, my name's on there. My son's name is on there. So 2.6 million members of the public and us put their names on this microchip, and they're actually etched onto there, right? It's not just like bits, ones and zeros, they're etched on. And it's in a hand-drawn bottle because this is our message in a bottle to this water world. There's a really beautiful poem that the US laureate Ada Limon wrote about the connection with water and life and humanity. And it's, there's all kinds of details on the website, so I encourage people to check it out because it's just really beautiful. And I love that that's kind of our little piece of humanity going out there into space.
I love that.
Yes. Very exciting and inspiring.
Mhm.
I could listen all day and we'd probably be on here for 5 hours and watch the clock. See, any other questions online? I don't see questions. Any other questions in the room? Any final thoughts from the panel before we adjourn?
Follow along. This is our,
Yeah.
this is exciting stuff. We at NASA, this is the kind of stuff that gets us all jazzed, that makes us so excited to be working on this kind of stuff. So, we hope to bring that enthusiasm to folks all around the world.
And remind me, the launch date is
October 10th.
Yes.
so mark your calendars.
Yeah.
Great. Well, I guess we'll end there today. Thanks to everyone for joining us here and online. This is our last press event of the conference, but be sure to check out the tip sheets we've compiled. I'll drop a link to that in the chat. And feel free to drop by the press room if you need anything. And of course, a copy of this presentation will be posted to AGU's YouTube channel today. Thanks, everyone.
Thank you.
Thank
so
you.
much.
Thank you.